The first part of this lesson today is going to be review of grade 10. So, tell me, when we're solving a system of equations, two lines in two space, there are three possibilities. What are they? What's one of them? Parallel and, no, perpendicular. I mean, they could be perpendicular, but that's not one of the ones that we're going to really worry about. That's a special case of one of them. Oh, parallel and what? Anybody? Parallel doesn't quite narrow it down enough for us. Collinear, or what we're actually going to say is coinciding. Let's say that, okay? So parallel and coinciding. So if I have two lines like this that are kind of on top of each other, like this, we call these parallel and coincident. What's the number of solutions to this system? Infinitely many, yes. Infinitely many. Okay, what's another possibility? Grade 10 was a long time ago, apparently. Come on, folks, we don't have time for this. What else can you have? They could intersect at a cross at a point, good. And in this case, they might be perpendicular or they might not. That doesn't change anything, right? So they cross, whoops, at a point. How many solutions? One. I probably should have finished that phrase before. Infinitely many solutions. And the third? Parallel and, what do we call it? Parallel and, anybody remember the word we use? So not, because if they're parallel and on top of each other, we've already got that one, but so they are parallel and, anybody remember? Distinct. Remember that? Parallel and distinct. Who was your grade 10 teacher? You guys don't remember that. I taught a lot of you in grade 9, but well, one of you in grade 10. So if they're parallel and distinct, how many solutions? None. No solution. Zero solutions. Part of what we're going to do over the next several days, today we're looking at intersections of lines. Two space is boring, three space gets interesting, but we're also using our new notation so the solutions look a bit different, and we have some added skills that we didn't have back in grade 10, which is part of the notation adds that, which makes our process of solving these a little bit different. So that's what we're kind of looking at over the next couple of days. But then we're going to look at intersections of other things. How can other things intersect? And they intersect in all kinds of different ways, and the way you solve them can be very different. And but one of the things that we're going to ask you to do a lot of is give a geometric interpretation and state how many solutions there are, and if possible, solve the system. So that involves three parts. And you got to state all three explicitly. You can't say they cross at a point, okay, but how many solutions is that? So the geometric interpretation would be they cross at a point. How many solutions? One, obviously, but you still state both those things, and then in that case, you'd probably solve it and find them. Does that make sense? Or you would say parallel and distinct, zero solutions. Or you would say parallel and coincident, infinitely many solutions. But we want you to say both. It's not assumed that because they're parallel and coincident, we know there's infinite. You have to state that. So let's try one. We're only going to do we do 1 and 2 space? Oh, we do 2 and 2 space. So the reason why this is different is because we don't have lines in scalar form. So how do we solve if we're given a different form? And in fact, I think I've mentioned this, parametric form is very useful for a lot of these things. So vector form and parametric form are going to be our two most useful in a lot of ways. Vector form is only moderately more useful for one thing. But parametric is the one that we want to actually do the solving with. It's the most useful for that. Vector form is useful for another thing that we're going to look at later. So if you have other forms, you're probably going to convert to do it this way. We won't give you scalar so that you solve like grade 10. Don't do that. We're not interested in that. We're not revisiting grade 10. We're using all grade 12 notation. Does that make sense? So off to the side here, I'm going to make a little note. Hopefully you got that copied down. Whoops, I don't want a big thick one right now. In parametric form, how do we solve? We just set x's from one of the lines equal to x's in the other line, and y's in one line equal to y's in the other line. It's that easy. And then you have a new system that you can solve. So my x's looks like this. 2 plus t equals 1 minus 2m. I'll call that equation 1. And my y's look like this. Negative 9 plus 4t equals 9 plus 3m. There are different habits that people have in terms of how you solve. So remember the two ways that we solve systems from grade 10, substitution and elimination. You can use whichever one you want. I could easily solve equation 1 for t. I could easily put my coefficients together, or my constants together, and simplify both. I happen to do it a bit of a different way, so I'm not going to do either of those two things, but you can do it like me, or you can do it however you want as long as you know what you're doing. That make sense? Good enough? Okay, so what I'm going to do is I'm going to take equation 1 and multiply it by negative 4. So I get negative 8 minus 4t equals negative 4 plus 8m. I'll call that equation 3. I'm going to rewrite equation 2. I don't really need to name that actually, but I'm going to get rid of that. Negative 9 plus 4t equals 9 plus 3m. And I always like to set up one of the parameters for elimination with a positive and a negative, because I can add really fast instead of subtracting negatives and that kind of thing. So I can always add really easily. So why not do it that way? So negative 8 plus negative 9 is negative 17. Negative 4t plus 4t is 0. I'm adding here, right? Negative 4 plus 9 is 5. 8 plus 3 is 11. Subtract 5 from both sides. Negative 22 is 11m. And m equals negative 2. What did I just find? What do you think? No? What did we find? I mean, M. Any thoughts? Any ideas?
So you found the value for t. No, I don't know what we found.
Daniel, what do you think?
We found the value that links x and y.
Very good. So we found the value of the parameter M when these two lines will cross. Normally what you would have found here is you would have found the x-coordinate or the y-coordinate. And we'd sub it into one of the original equations. Let's say we find x. Somebody might think, oh, we found x, because alphabetically m comes before t or something like that. But no, we didn't find x, we didn't find y, we found m. What is m? It's just a parameter. That's how parametric equations work. But the x and y in these things are these. These are x and y. M is a parameter. It's a new way of thinking. I know, like parametric form is new, right? But that's what parametric form is. It relates in separate equations through a parameter. That's what it does. So we found m. Do we need to find t? In fact, we don't. Normally, like I said in grade 10, you would have found x, you'd sub back into one of the original two equations and solve for y, and then you'd have your point. But what did we find? We just found the value m when these two lines cross, when they're equal. So what's going to be our next step?
Find x and y coordinates when m becomes that.
Yeah. So the lines cross when m equals -2. Therefore, x equals, and in this case, we have to sub in. So we must, because this is a question that always comes up, use line 2. Why do we have to use line 2? Because it's the one that has m. So m and t are different. T has a different value. We could find t if we wanted to by subbing in up here. We could sub -2 in here and solve for t. But we don't need it. We only need one of them. So we must use line 2. So therefore, x equals 1 minus 2 times -2, which is 1 plus 4, which is 5. And y equals 9 plus 3 times -2, which is 9 minus 6, which is 3. Therefore, the L1 and L2 cross at a point, and there's one solution, and the solution is 5, 3. So that, my therefore statement there has all three parts. Geometric interpretation or explanation. They cross at a point. The number of solutions, which is 1. I know it seems overkill, but it becomes important down the road when it gets harder. So we start practicing now. And the solution, since there is one, is 5, 3. You got to understand what you found here is not an x or y, and that you got to make sense of that to yourself and get that, right? It could be a good check to find t and sub t into there, and what should you get? Same point. So there's a quick check, and you might be able to do that relatively easily, mentally. You better get the same point. That's kind of what it means, right? Any questions about that? Not too bad, right? Pretty straightforward, pretty easy. Some of the thinking around this stuff is a little bit tricky, but the maths, again, still isn't too hard. Okay, so you can write this down or not. You may need to, you may not. When you're solving for t, now this is going to be, that's sort of useful. It sort of actually isn't, but anyway, we're going to remind you. This is from grade 10. Now, you might be solving for m, or you might be solving for t, or you might have a different parameter. I don't know, but that's not the point. You're solving for the parameter. In this case, we're going to call it t. And you get 0, t equals 0. What does that mean? Or you get 0, t equals some constant k, which could be anything. What does that mean?
last one is a solution.
So first one means what? So what geometric, which of our three scenarios is that?
Yeah, on top of each other.
Yeah. So this means they are parallel and coincident, infinitely many solutions. And the other one means, you already said no solutions, and what do we call that? Parallel and distinct. No solution. Zero solutions. Got that okay? As I said, we're not super interested in two-space anymore, but it's nice to build on what we already understand and look at this a little bit. Okay? Okay. However, example 2 is going to demonstrate to us that if you do these questions correctly and you actually think about it, you'll never get either of those situations. In this case, there are other cases moving forward where you would. In this case, when we're talking about lines intersecting lines, I'm going to say if you do it right and you actually think, you'll never get 0t equals 0. I shouldn't say never. That's not true, actually, now that I think about it. That's not true. Or 0t equals k, you often won't. There is one case where it'll pop up. And it means something, but it means something a little bit strange. Anyway, so what about this question? Because what does it say? The instructions here saying this is something we might ask you to do. Determine the number of solutions to the system without solving. If this was on a quiz or a test, not on the quiz, right? Because this isn't on quiz, but if this was on the test and you solved it, what do you think would happen? You would not get any marks because that's not the point of a question like this. So what can we do? What else about the system can we look at to determine which of the three, or start narrowing it down at least and getting closer towards what it might be?
You could start by looking at the direction vectors and seeing like if they're parallel or if they're like collinear.
Yeah,
Multiples of each other.
absolutely. That's right. So scalar multiples of each other, or which will tell us that they're parallel. So we can look at their direction vector. Direction vector of a line of each of them will tell us if they are parallel or not. If they're not parallel, then how many solutions do we have? One. If they're not parallel, they have to cross. If they are parallel, how many solutions do we have? We're not sure because there's two conditions where they're parallel. Okay, so but then we'll go further if that happens. So let's go ahead. I'm going to call this line 1 and this line 2, and I'm going to come up with direction vector 1. If this was in another form, it might be a little bit more work. This is why vector form is useful. So what do we notice? They are scalar multiple. And I like that, using that term, because people always get confused. Oh, do I take the dot product or do I do this? There actually is a way you could take the dot product and test, but it would be a disaster. It would be so much work. Why would you do that? Or the cross product. If you get the zero vector, means they're collinear. But generally speaking, we don't even need to do that. We just look, can I multiply one of them by something and turn it into the other? And sure enough, 2 times d1, this is how we're going to write it, equals d2. So they're scalar multiples. Therefore, line 1 is parallel to line 2. But we still don't know if they are coincident or distinct. So what do I do to move forward? Any ideas?
Just give TNS the same value as what it-
No. We could, if we solved it, that would figure it out, but without solving. So just because of the instructions, you can't. But there's still a better way, even if we were allowed to solve.
And not to pick fault solving, but like you could just look at the difference between the points that we're given.
Okay.
And then if that's a multiple of either of the slopes, then you can put they're on the same one.
Yeah, very good. There's actually even, I think, a bit of an easier way to do it, unless it's really obvious. Anybody have any thoughts what it might be? Again, it has to do with the points or the position vectors. What will be true if they're parallel and coincident? What will be true of the points? They have all the same points. So a point in one of them would be on the other line. If that's true, they're coincident. We already know they're parallel. If one point from one line is on the other line, then all the points are going to be on each other because they're parallel. If one point isn't, then no points are going to be, right, because they're parallel again. So all we have to do, so we are going to check the point 1, 5, which came from the position vector in the second line. And we know how to check if a point is on a line. Remember doing this? So I'll check the x first, and I get 1 equals negative 5 minus 6s. And then for the y's, I get 5 equals 19 plus 14s. What do we get? What's our interpretation of this? Yeah, so the s's are consistent. So the point is on the line. Therefore, L1 is parallel. I'm going to say it like this. L1 and L2 are parallel and coincident. And what were we actually asked to do? Determine the number of solutions. So we're not done yet. Infinitely many solutions. Any questions? So that was all in 2 space. What about in 3 space? So I kind of gave this one away, but part of what we're going to be doing over the next few days is thinking about others, not tomorrow, but after that, is thinking about other kinds of systems and what the possible types of solutions might be. So that was in 2 space. In 3 space, turns out there are 4. So I have a question for you. What are the 4? Are 3 of them the same as the ones in 2 space? Or not? Are you going to answer that question or you're asking something?
I'm
Answer kid, give me a minute. I want everybody to write this down and think about it for a second. So in 3 space, there's 4 possible outcomes. Are 3 of them from 2 space? Well, what do you think? In 3 space, can 2 lines, name one of the 3 space. Somebody do that? Simo, what do you want to start with? Pick one. Pick one of the things for in 2 space, what can happen? They can be parallel and distinct, let's say. Can that happen in 3 space? Yeah, don't see why not. Okay, so one of them is parallel and distinct. No solutions. What about parallel and coincident? Can that happen in 3 space? Of course it can. Same line, of course you could have the same line twice. I don't know why, it's not very interesting, but infinitely many solutions. What's the third one in 2 space? The exciting one, I guess. Cross at a point. Could that happen in 3 space? Sure, it could happen. Like, I got 2 pencils and I'm touching them together right now. They're like lines in 3 space that we actually exist in. They can touch. Of course. So cross at a point. And this is one solution. So then the challenge is, what's the 4th? How many people think they can picture it? So we got at least 1, 2. Anybody else think they have an idea of what might happen in 3 space? Okay, there's a few more. Good, 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 good. Okay, Daniel, what do you think?
They don't exist on the same plane.
So what would that look like?
They don't cross anywhere.
They don't cross anywhere, no solutions, and I like that description. They don't exist on the same plane. What were you thinking, Emery?
I was thinking like not parallel, but no solution.
Okay, good. I like it. Bradley, you had your hand up, sort of. What were you going to say? Because it's different to describe it, right? But
Yeah, they're not parallel, but they're also not crossing.
yeah, good. Anybody else want to add to that? We have a word for this. It's called skew. So this is what we call them. We call them skew. So the lines are skew. And this means no solution. Okay, so what does that look like? We're going to do a few examples, hopefully, if I can find them. Oops, I think I missed one. There we go. We're talking 3 space now. And here's what I'm going to say. The last example that we did where we used direction vectors to check if they're parallel, I think you always want to start with that when you're looking at lines and lines, because it can help us narrow down solutions. From the 4 possibilities, we're going to narrow it down to 2. And then what our solution looks like from there will depend on what we find. Okay, do you understand what I'm saying? So we're still going to, I would encourage you to always start by checking the direction vector. When you find that they're parallel, you're going to save yourself a lot of work and a lot of time. It's the efficient thing to do, but it's also the good thinking to do, right? To understand and make sense of what's going on here. So what is direction vector from line 1? Where do you get that in parametric form? By the way, you could rewrite this into vector form, but you would just have to know how to write the direction vector anyway. So I would say just get it from parametric, but you can convert however you want, obviously. It's coefficient of t's. So -1, -1, 1, and direction vector 2 is just given. 2, -4, 5. Therefore, what? Not parallel. Not scalar multiples. So we're going to say D1 not equal to KD2. Therefore, L1 not parallel to L2. So we've narrowed down our 4 possibilities to 2. They either cross at a point or they're skew. So what's that going to look like, and how do we solve these in 3 space? So first of all, I'm going to rewrite L2 in parametric. Again, you don't necessarily have to do this, but you have to be able to think of it in parametric. You don't have to necessarily show this step. I'll explain that more in a moment. So this is 7 plus 2m, 12 minus 4m, 17 plus 5m. Okay? And what we do is we write out, same thing for parametric, x equals x, y equals y, z equals z. Okay, so my x is going to be the x from L1, which is 3 minus t equals 7 plus 2m. So if you can do this from vector form, which I don't see why you wouldn't be able to, you don't have to show the work going into parametric. But that's what we're doing. We're just skipping showing that step. Does that make sense? But when in doubt, rearrange into the form you need. And you got to know how to go between all the different forms. Equation 1, equation 2, and equation 3. And again, from here, exactly what your solution looks like depends on what you want to do, how you want to solve it. But generally speaking, what we're going to do, this is the part you need to know, is you pick your favorite 2, turn them into a system together, solve that system, and check your solution in the other one. Okay? If you get a solution. You may not. So I'm going to pick 1 and 2. So I'm going to take equation 1 first. And then I'm going to go -1 times equation 2 just to flip the signs around. So -2 plus t equals -12 plus 4m. And then I'm going to add them. m equals 1. That's equation 4. In 2 space, we didn't have to go and find t. In 3 space, we do. Is everybody okay? Following this all right? So I'll go 4 into equation 1. So it turns out we got a consistent like x and y. We got a place where x and y cross. But that's only for x and y. We don't know about z yet. We're going to look at this in a minute. So we have to check in z. So we're going to check m equals 1 and t equals -6 in equation 3, which is z's. We're checking in z because we used x and y before. I hope you understand that, right? Yeah.
So the check for just x and y, and then like we're checking this in z. So it's like saying so that the two lines cross somewhere from some point of view, but not necessarily on the same thing.
Yeah, very good. We're going to look at that in a moment. Yeah. We're going to actually look at it visually in a moment, but very good. That's exactly what that means. So a couple things I want you to watch carefully here. When I found m, I hope it's obvious that because I started with x and y, I've got to sub into one of those two to find t. Don't sub here into equation 3 or into z, right? We only use that at the very end. So we find a solution for m and t with any two of the three, but we got to stick with those, whichever two we pick. Pick whichever one looks easiest to you. If one's already solved for t, if it just says t equals and you can sub it straight in, do that. Like, I don't know, right? And then you have to check that in the other one that you haven't touched yet. And that's our check. And what do we find? Left side equals right side, so what? What do you think? Yeah, so we got it. It works for x, it works for y, and it turns out it works for z. Okay, so therefore, L1 and L2 cross at a point. There is one solution. I know it seems redundant. You said it crosses at a point. A point is one place. And then we say there's one solution. And then we're going to say what the solution is. And those are like three different ways of saying the same thing. I know, but you got to say all three if your instructions are, which they often will be, give a geometric interpretation of the system, state how many solutions there are, and if possible, find the solution. You have to do all three. You can't just assume that one means all the others. Okay? And so how are we going to actually find our point? Sure, sub in m or t into whichever one you want. Okay, so we can do m into L2. So we're going to sub m equals 1 in L2. So to find x, I get x equals 7 plus 2 times 1, which is 9. Y equals 12 minus 4m, which is 8. And z, oops, 17. Therefore, the solution is 9, 8, 22. So that's what it looks like if you have the two of them crossing at a point. Everybody got that okay? Let's see graphically what these look like once you have this copy done. Okay. So if I only have one line, or sorry, if I have two lines that are coincident, I mean, obviously that's what it would look like. It would look like one line. If I have two lines that are parallel and distinct, there you go, that's what it looks like. Now, from this perspective, they look like the same line, but everywhere else, I can see that, I mean, they sure look parallel, and they are, by the way I've designed it. And in 3-space, that's what it would look like. This one is skew. So like Daniel was saying, from one perspective, it looks like they cross. The x's and y's are good. I found a solution for x and y, and you can see that visually, but it didn't match z. Now, in this case, I don't know which one's which, but that's exactly what that would look like. But you could also not find a solution for x and y, and in that case, your interpretation, you'd be done. So not every solution looks exactly the same. And then what would it be? For some reason, I can't. There we go. Nice. What would it be if they cross at a point? There you go. So there's no way that I can look at this where they don't. And I mean, it's a little bit hard to see, but you can trust me, they do cross at a point because I designed it that way. They're not skew, these two. Okay, any questions? We got two more examples. So again, you could rearrange these into whatever form you like. Put them both in parametric if you want. Put them both in vector form first and then parametric, like whatever you want. But what you need to be able to do is, you may need to be able to convert them. You certainly need to be able to get direction vectors out of them and get points out of them and know how to do that. And really, if we're going to be setting them equal to each other, you got to be able to do the parametric part. So I'm going to start with D1 and D2. I would recommend, as I said, always starting with these. What's D2? Who remembers? So it's the denominators. So what's our conclusion? Not parallel. So if you think you can skip this part, then go ahead. Otherwise, I'm going to do this part. I'm going to show it. Write out the parametric for each. I want you to try that, though. Now there's a little bit of trick in one of these. Have you finished? Has anybody finished? Did you catch the trick? The trick is like this. It's x minus x, x naught over m1, let's say. Y minus y naught over m2. m1, m2, and m3 are the components of the direction vector. So the trick is this one's not in the right form. What should it be? Well, I'm going to factor out a negative, and I'm going to put it on the bottom. So this should be plus 4 minus 2. And in fact, we had that mistake earlier, but it didn't matter. This direction vector should be negative 2. But it didn't matter over here, but it matters now.
Can we go both T or
Oh yeah, no, we shouldn't. Thank you for catching that. Definitely, you can't do that. So we got to come up with another one. Often we use M. You can pick whatever you want for your parameter. Okay, so we already know they're not parallel, so now we just have to write out our equations and start solving. Okay, and I'm going to pick x and y again, because to me it doesn't really matter. So negative 3 times 1 gives me 6 minus 3t equals negative 9 minus 15m. Rewrite equation 2. And add them. I got negative 19 over 20. I'm going to sub that into equation 1 to find t. So I got 5 minus 19 over 4, which is 20 over 4, minus 19 over 4, which is 1 over 4. What's our next step? Yeah, check it in Z. Check it in equation 3 in this case. Again, that's because I chose 1 and 2 to start with. So what happened in this case? My left side does not equal my right side. So we got something that worked for x and y, but not z. Therefore, Zach, what do you think? We already said they're not parallel. Remember when we said that? So if we go back, not parallel, so they're not parallel and distinct, they're not coincident. So what are our two other options? They cross at a point or they're skew. So what do you think? Why do you think that? Yeah, X and Y worked, but then what about Z? It doesn't matter? Compare to this to the last one where the Z worked out as well. You think they're skew. I think they're skew as well. This is what this means, okay? So check out the last example. When left side equals right side, they cross at a point. Therefore, but in this case it doesn't. L1 and L2 are skew, and there's no solution. Okay, we got one more to do. We only have 4 minutes to do it, but we can get it done. It's shorter. Why is it shorter, Daniel? Yeah, they're parallel. You can tell by looking at them that they're parallel. Okay, so I'm going to do this quickly. So I get each direction vector, 1, 1, 1, -2, -2, -2. -2 times direction vector 1 equals direction vector 2. Therefore, L1 and L2 are parallel. But we don't know yet if they're coincident or distinct. So just like we did before, we're going to find a point on one of them, which if you think about putting it in vector form, you'd have a position vector to a point. So we have a point. Check that point in the other line. So I'm going to check 1, 2, -4. I hope you can see where I got that from in L2. And I got to check it in every single one. So 1 equals 2 minus 2t. And 2 equals 3 minus 2t. And -4 equals 8 minus 2t. T is inconsistent. Is not on line 2. Parallel and distinct, no solutions. Your practice is just questions 1 and 2 from the worksheet that was posted.